Welcome. Let me say something about the beautiful theorem in geometry, the Riemann Hurwitz theorem. This is actually work from 2012, 2013, done with Thomas Tucker from Colgate. But as you see, it is almost trivial and somehow feels like pissing on the grandmasters of geometry if you look at it in the discrete. But it's often the case that in the discrete theorems are much simpler than in the continuum, where you need more assumptions and some regularity. And but the setup is very general. We have a simplicial complex and we look at the subgroup of the automorphism group, and we can take the quotient. So there are two pictures for this. One picture is that you see this G over A as an orbifold, and especially if G is a manifold, or you can see G as a branch cover over G over A. Now there's a difficulty with the structures, and that's also what we thought about, and we were not so quite sure what to do, is that if you look at the G over A, then this is no more a simplicial complex in general. But that's not unusual. If you look at the product, the Cartesian product of two simplicial complexes, that's not a simplicial complex. If you look at level surfaces, that's not a simplicial complex. So you have to go a little bit beyond that and look at delta sets. I talked a lot about delta sets in the last couple of years. It's a very beautiful structure. It produces a topos, so it's very general. You can do all kind of operations in it, and it generalizes the sets, it's the topos of sets. And so we have in the set theoretical setup, we have a beautiful lemma which is called the Burnside lemma, which tells you something about dynamical systems. So you have a group A, that's kind of at the time acting on a space X, and then you are interested in the cardinalities of the equivalence classes. How many equivalence classes are there? How many orbits are there? And then there is this formula here which tells you that you just take the number of equivalence classes times the number of group elements is a sum of cardinalities of fixed point sets. So that's a Burnside lemma, and if you reformulate this a little bit, take out the transformation which is the identity, then we get here X, and all the transformations which are not the identity, non-trivial dynamical systems and dynamics. The non-trivial dynamics is encoded here, and that then reflects in the ramification points which you have in the geometry. So let's just look at some. The best is to look at some examples. Maybe first this example here is a nice example which shows that the circle is a ramified cover over the interval. So, and then of course there are ramification points here, and these ramification points count when you are looking at when you count the things up. And Euler characteristic is nothing else than counting. And that's kind of the observation. What you have to do to prove this, we have just to look at each level, at each dimension, and we apply just Burnside for each of these sets GK, which you appear also in a delta set framework. So what you have is then we just write down Burnside, and you multiply it by -1 to the k, where k is the dimension, and then you add it up and you reinterpret this now as the Euler characteristic of the quotient times the group size is the Euler characteristic of the whole object, plus correction, which is the ramification story. Now, in the case when there is kind of, if you have a fiber bundle where you have a fiber bundle and you just have a principal group A and you quotient it out, of course, then it's just the product and there are no ramification points. So an example of that is if you take the projective space in n dimension, and then you see the universal cover you see as a ramified cover, but the ramification is trivial because there is no there are no non-trivial fixed points, and so you have this also this formula for the Euler characteristic of a n-dimensional projective space, which is just half of the Euler characteristic of a sphere. So it's kind of like a half sphere, and so that's the Euler gem formula, and that's then a consequence of this. Maybe just in general, just to illustrate that this is not necessarily, a nice space. And if you take the quotient, an orbifold, like a manifold, and you take a finite group action and you quotient, it doesn't give you a manifold in general. Also here we don't even have a simplicial complex. Simple example is if you take Cn and you take the full rotation group Zn. So this is C4, for example. You take all this, the full group. What you get is you quotient the vertices. That's no problem. That gives a point, but the quotient of the edges gives you a self loop. So you have something like a quiver. But then that's actually kind of where the difficulties start a little bit. If you interpret it as a delta set, you're fine. But in the quiver setup, I worked about this quite a bit on spectral level. You want this to actually treat this as vertices, so that you have the calculus, and that calculus works like for graphs, especially that the Kirchhoff Laplacian is positive semi-definite. But that's the story here, which maybe that example is here kind of a beautiful example, which is not so obvious, right? What we have is the figure 8 structure, which you can see as a ramified cover over the path graph. So what you have is now in this case we can take, not the group generated by one element, but the group generated by two elements, so that the group cardinality is the order of the group is 4. This is C2 square. You can either flip here or flip here, and then you can look at the ramification points. So in this case, these points have ramification index 3 because they are fixed by 3 group elements. Actually, all group elements except the identity we don't count, right? We never count the identity. And then for the edges here, you can just see that the edges have a ramification point of 1 because they are always only fixed by one of the group, non-trivial group elements. And so if you count everything up, you get the Riemann Hurwitz story. So the upshot is Riemann Hurwitz is essentially trivial if you look at it just from this perspective. And that's what I wanted to say today. Happy birthday, USA.